Hi everyone, welcome to Bold Conjectures with Paras Chopra. Today I'm with Dr. Stephan Guyenet, who's a researcher and science communicator in the field of neuroscience of obesity. He has written an excellent book on the same topic, The Hungry Brain. In his book, he explains how the brain is the central organ responsible for gaining weight and body fat. Stephen finished his PhD in neuroscience from the University of Washington, and then he spent 12 years as a full-time researcher exploring the science of obesity and its link to the brain. Stephen is also the founder and director of nonprofit called Red Pen Reviews, an online publication where he and his fellow researchers review popular nutrition books on their scientific accuracy. Nutrition is a field with lots of unfounded claims. So I'm very grateful for Stephen and the team to put out this effort for sifting scientifically grounded nutrition from pseudoscience. So today my plan is to explore with Stephen the neuroscience of why we get fat and what we can do to stay fit. Welcome to the podcast, Stephen.
Okay, thanks for having me.
Fantastic. So I wanted to start with the very basics. I know everyone talks about obesity, but I'm not sure if people understand exactly how it's defined. So can you help everyone understand what is obesity, and generally why should anyone care if they're obese or not?
Yeah, so at the simplest level, obesity is excess fat on the body. And how do we define what is excess? So essentially, excess is an amount that is thought to impair health and or quality of life. And so there are different ways that this has been defined, different cutoffs for obesity. And one common measure that's been used is the body mass index, which is weight divided by height squared. And it typically is, so it's essentially your weight corrected for height is a way to think about it. And so typical cutoffs are a body mass index of 25 or higher, or 25 to 30 is considered overweight. And then 30 and higher is considered to have obesity. And there are different classifications even over 30. So 30 to 35 is class 1 obesity, 35 to 40 is class 2, 40 and higher is class 3. And so those are the ways that, those are common ways that obesity is defined. Body mass index has limitations because it doesn't really tell you whether the weight is fat or muscle. And so someone who is particularly muscular or has particularly low muscle mass could actually have obesity from a fat mass perspective, even while not having a very elevated body mass index. And in that context, particularly, we know that that can apply to South Asians, particularly. So that's relevant in this context. And so the reasons why we should be concerned about it are because it increases risks of health conditions, particularly type 2 diabetes, which is a very weight sensitive condition, but also cardiovascular disease, certain types of cancers. And then beyond that, I think something that is perhaps even more relevant to most people is quality of life. So it impacts your physical performance. For example, a child with obesity may have difficulties playing in the same way as a child who doesn't have obesity. Adults may have difficulty engaging in sports if they have obesity, and it affects people's love life. It affects their perceptions of themselves. It affects their life satisfaction. And so there are a lot of very kind of tangible day-to-day effects of it as well, in addition to the long-term health consequences. So I think obesity at this time in history is one of the primary health challenges that industrialized nations are facing.
Right. You make so many excellent points. Let me just pick a few of them. One of the points you made was BMI is sometimes ethnicity specific. So especially for South Asians, the BMI guidelines are way different. And I came across this fact only a couple of months back, and I was just super surprised because I'm a South Asian myself, particularly East Indian ethnicity, and in that context, my BMI was I think 24, and I was pretty happy that way. But when I realized that for South Asians, 24 is actually overweight, and after 25 it becomes obese, it was sort of like a completely perspective shifting for me. And I do think, given the obesity in India and South Asia, I do not think my experience is that most people don't realize that we tend to put a lot more body fat for the same amount of weight as compared to, say, Caucasians or the Western sort of European descent ethnicities.
Yeah, that's right. And I think part of the issue is that as well is that it doesn't take as much fat for the average South Asian to be at higher risk of type 2 diabetes and other metabolic complications. There's a lot of genetics that goes into how your body responds to fat. And so essentially some people have an ability to store more fat in a healthy way, so they can accumulate a higher level of fat without it spilling over onto other tissues and causing metabolic havoc. Whereas some other people, their fat tissue just doesn't have the ability to store it as well, to hang on to it as tightly, and so it kind of spills out and affects the other organs. And that can happen to people of any race. However, it is more common in people of South Asian origin. It's like it just doesn't take as much fat for that to start causing metabolic complications. So that's another reason for the lower BMI cutoffs for South Asians.
Right, and I think in your book you explain how these cutoffs were sort of, if I'm recalling correctly, I mean, these cutoffs are there because researchers have seen sort of almost a correlation of BMI with different increased propensity for different health conditions, right? Like if you have BMI 25, you're much more likely to have diabetes versus BMI 20. And it's also like a misnomer to think as soon as you get below 25 cutoff or the normal range, everything is okay. But my understanding is that it's actually just linearly related. So lower the better.
Yeah, I think what really matters is body composition, how much fat you have, how much muscle you have. And body mass index is just kind of a really rough way of assessing that. So, someone with a low body mass index is not necessarily healthy, but it is an indicator that they probably aren't carrying as much fat on their body. But there's a lot of context. And I think when someone is thinking about their own body mass index, I think it's good to also consider the context of, looking at yourself in the mirror and thinking about, do you work out regularly? Do you do strength training? Because that context can help you understand what your body mass index means. Does it mean that you have elevated muscle mass? Does it mean you have elevated fat mass? What is your body shape? Do you particularly have a lot of fat in your abdominal region, your stomach region, which it would correlate with extra risk? So I think there's, body mass index is kind of a crude screening tool, but in my opinion, if you just pair that with a mirror and some common sense, you can get a pretty good idea of where you stand.
Got it.
But I think if we're talking about excess fat mass, yes, I think that there is a relationship where the more of it you have, the higher your risk of certain conditions are. And that's particularly true for type 2 diabetes. Type 2 diabetes, as I said, is very sensitive to fat mass and excess energy intake. But it also impacts other things like cardiovascular disease, risk of certain cancers, and then all of the related metabolic conditions like liver problems and hypertension and stuff like that.
Got it. How well do we understand is it like a causative link, obesity and different health conditions, or there is a correlation, but we don't understand the mechanism? How well as the sort of the state of the art in the science do we understand what exactly is that fat does in the body, which makes us unhealthy?
Yeah. So I think it is causal. I think excess body fat does cause these health problems. However, I don't want to state that with 100% confidence. And I also don't want to imply 100% certainty that that's the only mechanism. So I think research is ongoing on this, but I feel pretty convinced that it is a cause and effect relationship from fat mass to health problems. And basically the way I think it works is that insulin resistance and resulting increase in insulin secretion. So insulin is a hormone secreted by the pancreas that's really important in metabolism. People think of it as regulating blood sugar, but it regulates a lot of other stuff as well related to the energy fluxes in the body. And that seems to be a real cornerstone of metabolic dysfunction and health problems. So when your insulin stops working as well. So you become insulin resistant, you get higher levels of insulin secretion, and that contributes to type 2 diabetes risk, cardiovascular disease, cancers, all of those health conditions at a minimum seem to correlate pretty tightly with that type of metabolic dysfunction, but we think that's probably causal. And if you look at what's causing that insulin resistance, a key factor seems to be what I call energy poisoning. And what I mean by that is that the tissues in your body are being exposed to excess energy in the form of glucose, fatty acids, amino acids. Those are the three primary types of energy circulating in the body, particularly the glucose and fatty acids, which is carbohydrate and fat. And insulin resistance is essentially a cellular defense mechanism against excess energy, because insulin is a hormone that tells your cells to take up glucose. And so when your cells are full of energy because they've been exposed to too much, they say that's one of the ways that they start limiting their uptake of additional nutrients. And you can see that there's a lot of evidence to support this. So if you take cells in a petri dish and you expose them to high concentrations of glucose, fatty acids, or amino acids, they will develop insulin resistance. If you infuse high levels of glucose, fatty acids, or amino acids into a person via the bloodstream experimentally, they will quickly develop insulin resistance. And if you then cause someone to, if you reduce their energy intake, they will increase their insulin sensitivity if there's someone who carries excess fat. So basically, overconsumption of energy relative to your needs, it creates this energy load on your body, and your fat tissue can handle that for a while. As long as your fat tissue is healthy and you don't have too much of it, it can absorb that extra energy and protect the rest of your tissues from that excess energy. But once your fat tissue starts to reach its capacity, which seems to be very genetically determined, then it just can't expand anymore. And that excess energy is not being mopped up, and it starts to accumulate in your other tissues. And you see this in the form of what's called ectopic fat deposition. So you see that fat starts to accumulate in the liver, starts to accumulate in the pancreas, in the muscles, in places where it's not supposed to be. And that correlates a lot with insulin resistance. It's a marker of that excess energy exposure. And then at that point, your tissues are just overloaded and they're doing everything they can to refuse this excess energy. But it's still kind of being crammed down their throats because there's nowhere else for it to go. And so that causes insulin resistance. It probably causes your pancreatic beta cells, which secrete insulin, to become dysfunctional once they start to become dysfunctional once they're exposed to excess energy for a long time. And then they stop secreting insulin effectively. And then the situation just gets even worse, spirals out of control. And then you have type 2 diabetes. So that's kind of what I think is the main thing that's happening. And I could go in more detail on the evidence, but I'll just leave it there for now. And if there's anything you want to follow up on, I'll give you a chance to do that.
Yeah, I mean, it's what you describe is essentially if we eat a lot, all the energy that's been taken up by the cells, and insulin gets secreted in response of the sort of the energy that needs to be metabolized in the body. But after a period of time, since so much of energy is coming in and cells cannot take all of it, there is, say, unmetabolized energy out there in the body, say in the bloodstream, and the insulin keeps on rising, and the cells have to become insulin resistant because they just can't take anything more. For some reason, I always thought it was the other way around, which is maybe the beta cells in pancreas, they start becoming dysfunctional and sort of increase a lot of insulin, and the cells have to become insulin resistant because there is a lot of insulin out there. But what I hear from you, it's probably the other way around.
Yeah. So, I mean, this is a nuanced area. So it could be both. It's not necessarily one or the other. Those are not mutually exclusive. And there is some evidence for the scenario that you said. I tend to think the main factor is the one that I described. And if you look at the genetic studies in humans of the genetics of insulin resistance and the genetics of type 2 diabetes, what you see primarily for insulin resistance are genes relating to adipose tissue capacity. So that suggests that the main determinant of insulin resistance in humans is how well your adipose tissue your fat tissue can mop up that excess energy that most of us are consuming in industrialized societies, rather than genes that cause people to oversecrete insulin. So those are not primarily the genes that are popping up. And if we look at the genes that relate to type 2 diabetes, they're mostly genes that affect either insulin resistance or that actually reduce insulin secretion by the beta cells, or that have some kind of effect on beta cell development or function that would be expected to reduce their resilience to metabolic insults. So I think, as I said, I think the scenario that you outlined is totally plausible and could be part of the explanation. I think right now the evidence is primarily pointing toward this scenario that I described, but they're not necessarily mutually exclusive.
Got it. So maybe the driving or the major factor is insulin resistance happens first, and then dysfunction of beta cells causes less and less insulin to be secreted, and then all other sort of metabolic conditions are a downstream of these two things.
Well, I think type 2 diabetes, the scenario that you just described is type 2 diabetes. So basically what has to happen is, or what typically happens is, you get insulin resistance, and then after a while, your beta cells just kind of fail and they can't secrete enough insulin to keep up with the insulin resistance. And it's kind of that 2-hit scenario, because some people, they can become insulin resistant, but their beta cells just keep cranking out insulin, and they're making enough that they're able to maintain metabolic control, and their beta cells never fail. They just stay super insulin resistant and they're fine. I say they're fine. What I mean is they don't develop type 2 diabetes, but that person could still have the metabolic syndrome. So, they could still have abdominal obesity, they could still have hypertension, they could still have blood lipid abnormalities. So it doesn't mean you're off the hook, but if you don't experience that beta cell failure, you're not going to develop type 2 diabetes specifically.
Got it. And all the conditions that you described, even if your beta cells are fine, they're because of elevated insulin levels, because the body's insulin resistance, like hypertension or other conditions of such sort?
Yeah, that's a great question. And I really wish I could give you a definitive answer. It's been a while since I've reviewed the evidence on this. I know that some people, like Gerald Reaven, for example, the Stanford endocrinologist who was the discoverer of the metabolic syndrome, he believed that elevated insulin secretion in itself was a key driver of the health consequences of insulin resistance. So, but I think it might be more complex than that. I think maybe some of the problem is due to the elevated insulin. Some of it is due to the insulin resistance. But it's been a while since I've reviewed the evidence, so I'm also a little fuzzy on where exactly the evidence stands there. But I will say, I think there are good arguments to be made by good arguments have been made by good researchers that the elevated insulin itself is at least part of the problem.
Got it. All right. So we know that excess body fat is just generally not good for health. And we also know that if you keep on consuming more calories than the body needs, it gets converted into fat. I wanted to get into why we eat so much and why we get fat, but maybe perhaps you can spend some time talking about how everything that we eat, the excess calories, how does it ultimately just end up into the fat cells, irrespective of what we eat?
Yeah, so it's essentially the types of foods that we eat have only a pretty modest impact on the amount of energy that our bodies burn. And so, and it's not nothing. So if you go on a very low carbohydrate diet, there is some evidence that your body might start burning a little bit more than it did before. However, within the range that people are typically eating in, the effect size is trivial. So basically, if your body is burning the same number of calories, then the amount of the change in the energy content of your body at the end of the day is going to be determined by how much you're eating relative to how much you're expending. And if you're eating more than your body needs, more than your body is expending, that energy has to go somewhere. And ultimately, there's only one place for it to go, and that's fat mass, because your body fat, your fat tissue is the only place in your body where large amounts of excess energy can go. There's no other energy storage site that has nearly the same capacity. So we do have some carbohydrate stores in the form of glycogen, but that's the kind of thing that can buffer like a day or two of energy and carbohydrate intake, but it barely contains a tiny fraction of the amount of energy that your fat tissue contains and can contain. And so your fat tissue is really that long-term storage and long-term buffer of long-term energy intake. And so that's the place where it goes. And the way this happens in the body mechanistically is that when you eat excess calories, what your body will do is it will take it'll take a portion of the fat that you ate and it will shuttle that directly into your fat tissue. So it almost doesn't depend, it almost is irrelevant what you're eating, how much fat and carbohydrate, et cetera, unless you're eating like almost zero fat and there's literally like not enough to cover that excess, that intake that you took, which is very, very rare to have a diet that's that low in fat. Your body simply takes that dietary fat, whatever covers that excess calories that you took in, and just shuttles it right into your fat tissue. And so on a mechanistic level, that's how it works. And we have lots of studies demonstrating this, that energy intake is a powerful determinant of changes in fat mass.
Got it. And even if we are eating, a lot of carbohydrate, a mix of carbohydrate and fats, my understanding is that even carbohydrates get converted and stored as fat. And perhaps if it's like a very, very high protein diet, maybe even proteins get broken down and stored at fats. Am I correct?
So carbohydrate can get converted into fat by the body, but typically it's only a very, very small amount of it that does under normal conditions. It's really only under pretty extreme experimental conditions that a significant amount of it starts to be converted to fat. So, like, for example, feeding people experimentally on extremely low fat, high carbohydrate diets that are really high in simple sugars. That kind of a diet, you'll start to see more de novo lipogenesis is what it's called. So carbohydrate to fat conversion primarily by the liver. But under normal conditions, it's really pretty negligible. But instead, what will happen is your body will just shunt dietary fat into your fat tissue. And so if you let's say you are eating a diet, just for simplicity, let's say half carbohydrate and half fat, 50-50, and you're in energy balance. So you're eating the same amount that you're burning. And then you add 100 calories of carbohydrate on top of that. So now you're eating 100 calories more than your body needs, and that's coming entirely from carbohydrate. What your body will do is it'll just take 100 calories of the fat you're eating, and put that into your fat stores. So eating more carbohydrate definitely does increase your body fat storage, but it does that by displacing fat oxidation.
Interesting.
If that makes sense.
Yeah, it makes sense. So it's sort of like the body first utilizes all the fat that you're eating for storage of fat. But if that's so, I'm curious, why is this ketogenic diet so popular, where it's just excess fat and people believe, and I think there have been success stories also of people losing weight on ketogenic diet?
Yeah, absolutely. So the reason is that their energy intake goes down. So their total energy intake declines. So that you don't store fat if you're in negative energy balance, if you're eating less than you're burning, regardless of whether that's fat or carbohydrate. So if your energy needs are 2,500 calories per day and you go on a ketogenic diet and now you're only eating 2,000 calories a day, then it doesn't matter that that's mostly fat. You're still going to be losing body fat because you're in a calorie deficit of 500 calories per day. And so it really, if you look at the studies that have highly controlled diets, like metabolic ward studies, and then they're measuring fat mass changes, it really seems to not matter at all. It doesn't matter measurably whether the calories are coming from fat or carbohydrate. All that matters is the energy balance. And I'm not saying, it's possible that if we did bigger studies, longer studies, maybe there would be a difference that could be detected. But under the conditions that have been studied, both overfeeding and underfeeding, there's really little or no detectable effect of fat versus carbohydrate that is independent of the calorie value of that.
Got it. I know in some of your review papers you talk about models of obesity. So generally, again, the natural question is, if eating more than what the body requires is so bad for health, why are we doing it? A lot of us are overweight or obese. So why is that so? And I know I'm setting you up for this very, very broad topic, but this is what this is sort of the gist of what I was trying to get to in the podcast.
Yeah, absolutely. I think this is really a key question and a great starting point, because it doesn't make a lot of sense, right? Like, nobody wants to overconsume. People don't want to have overweight. They don't want to have obesity. And yet we do that. Most of us do that every day. And so how is that possible for us to not want to do that, and yet we do it anyway? So I think it really illustrates that our brains are composed of different functions, and those functions are not always agreeing with one another, right? So there's a part of your brain that wants to remain slim and wants to remain healthy and would prefer to implement behaviors to do that. And then there's another part of your brain that just wants to eat too much. And those two parts of your brain are disagreeing with each other, right? And the one that wants to eat too much is usually winning. And so how exactly does that work? I mean, first of all, that's kind of an interesting observation in and of itself, right? Because we kind of like to think of ourselves as this, unitary mind that is thinking and making decisions. But I think it's more complicated than that. I think we have different parts with different motivations that are competing with one another. And essentially, one way to think about this is using Daniel Kahneman's framework of System 1 and System 2. System 1 are the parts of our brain that are automatic and intuitive and mostly non-conscious. So we're not really controlling them. We might experience some of their outputs, but we're not really controlling them. And then there's System 2, which is the conscious, effortful part that we use for thinking and willpower and the things that we do control consciously. And the parts of our brain that cause us to overeat are System 1. Those are things like, what part of your brain makes you feel hungry? You're not in control of that. You experience hunger, but you don't decide, I want to be hungry now, and then turn that on, right? That's just something that arises that you experience. And the same with a craving. If you see freshly baked cookies in front of you, you don't consciously flip a switch in your brain that says, I want to start desiring these cookies now, right? That's something that arises on its own because of sensory inputs that are entering your brain and triggering something non-conscious. And so there's a lot of stuff like this in our brains that, if you think about it, makes logical sense, right? That's what's going on, that there's all this non-conscious stuff that's impacting our eating behavior. But I think most of us just haven't really sat down and thought about that and thought about the implications. And so my book is all about what are these non-conscious brain regions that are impacting our eating behavior in such a way that drives us to overeat. And so it's the book is kind of an attempt to catalog and describe these systems. And I think, neuroscience is really complicated. So there's no way that I could cover everything in one book, even if I knew how it all worked. But I've done my best to cover the important stuff in the book. And so I think there are different reasons for why we overconsume, and we can put those into two main categories. And again, the framing here is I'm talking about non-conscious brain regions that in the modern food environment push us to overconsume. That's kind of the framing here. The two categories are what we can call homeostatic systems and non-homeostatic systems. So homeostatic systems are systems that evolved to try to regulate our energy status. So those are systems that regulate like our body fat mass and regulate our appetite on a meal to meal level. Like those systems are trying to make sure that your body has the right amount of energy in the fat stores, in your digestive system, but not too much. That's what those systems are doing. And then the non-homeostatic systems is all the stuff that makes you eat for other reasons. So reasons that don't have anything to do with energy, like, for example, the reward system that decides that certain foods are particularly valuable and creates a motivation to eat those foods. So, for example, we're more interested in eating, like, let's say, French fries than celery sticks, right? Like French fries or ice cream, those are more appealing foods to the brain than celery sticks. If you put ice cream next to celery sticks on a plate and hand it to a kid, which one are they going to eat? So there are intrinsic differences in the motivational value of foods to the brain. And so that's an example of a non-homeostatic system. And so let's start by talking about the homeostatic systems. So we can break that down into two categories. One is the short-term regulation of energy status, and one is the long-term regulation of energy status. So the short-term regulation is the circuits primarily in our brainstem that regulate our satiety. So the fullness that we experience, satiation and satiety, the fullness that we experience as we consume a meal. So we sit down to the meal, we feel hungry, we start to eat, and then with each bite we take, our motivation to continue eating declines a little bit, right? And then at some point, we get to the point where we're not motivated to eat anymore at all, and we terminate the meal and do something else. So that point is called satiation. And then we're not interested in eating for a while after that. We feel full. That's called satiety. And so there are brain circuits that regulate that. We intuitively kind of think, oh, my stomach is full of food and that's why I don't want to eat anymore. But actually, usually your stomach's not even close to full. Human stomach is huge. It can usually eat a lot more than we typically eat. What happens instead is that your brain decides that you've had enough and it sends a signal. And that's a very complex regulated process that occurs, as I said, primarily in the brainstem as a result of ascending neural signals, primarily from the vagus nerve, but also from other sensory systems throughout the digestive tract. And so, as it turns out, different foods impact that system in different ways. So if you're eating a food that is very calorie dense, In other words, it has a lot of calories per unit mass or per unit volume. So think about like something like cheese would be very calorie dense. Something like a fruit would be less calorie dense because it has a lot of water. Chocolate, very calorie dense, right? Those foods do not create as much satiety and satiation per unit calorie as foods, that are lower calorie density. So a food like a piece of fruit that has a lower calorie density, more water, so the calories are diluted. For the same number of calories, it stretches your stomach more. And that is part of the signal that goes up and gets processed in your brain and makes you feel more full per calorie that you've consumed. Also, higher protein creates more satiety and satiation. Higher fiber as well. And higher palatability creates lower satiety and satiation. So the better something tastes, the more your brain is like, I think we could have more of this. And it kind of takes the brakes off a little bit. And so what ends up, if you put all this together, what ends up happening is foods that have high calorie density, low protein, low fiber, and high palatability, those are foods that per unit calorie don't generate much satiation or satiety. So those brain circuits in your brainstem that determine all this stuff, they're just not firing as much per unit calorie. And so you have to eat more calories to reach that point where you feel full and your motivation to continue eating ends. And since that feeling is what we typically use to determine whether we've eaten enough, I mean, normally we just sit down and we eat till we're full, right?
Yeah.
You can reach that point with dramatically different number of calories depending on the type of food that you're eating. And so those properties that I just described correspond to highly processed, calorie dense, refined industrial foods. Things like pizza and French fries and cookies and cake. Those are the types of things that are going to create very little satiety and satiation per unit calorie, and that are going to just naturally lead to an overconsumption on a meal-to-meal basis without you even noticing. Conversely, more lower calorie density, more natural, unrefined foods like fruit, fresh meats, eggs, vegetables, whole grain foods, those types of foods will tend to create more satiety per unit calorie, and you will consume less on a meal-to-meal basis without even noticing or thinking about it. So that's the relevance of that short-term regulation system. Then on the long-term regulation, we have what's called the lipostat. And this is a system in the hypothalamus that regulates your body fat mass. And so essentially what it does is it measures the amount of fat on your body using the hormone leptin that is secreted by fat tissue in proportion to how much fat you have. So the more fat you have, the more leptin you have in your blood. Your hypothalamus measures that and decides whether it's enough, essentially. And if it's enough, then you're cool. But if it decides that it's not enough, then it starts to activate a starvation response. Makes you feel hungry. It makes you feel more motivated to eat calorie-dense foods. It biases your attention toward food and eating rather than other activities. It can curtail your energy expenditure, so lowers your metabolic rate to conserve energy. And it does all that, and it shunts the energy into your fat tissue. And it keeps doing that until your leptin goes up enough so that it's satisfied. And so that's a key reason why it's hard to lose fat and keep it off, is that the system opposes fat loss. And the cruelty of it is that this system seems to work just as hard in people with obesity as lean people. So the system in people with obesity has decided that obesity is the new normal, and it's going to defend that state against fat loss. So you see that people with obesity, when they lose weight, they experience this starvation response activated by the brain, just like if a lean person tried to lose weight. So the body is saying, no, I don't want to do this. You're starving yourself. Even though in reality, a person with obesity is not starving themselves by going on a diet. They still have excess fat mass, but the brain perceives that the person is starving themselves because of how this regulatory system works. And so essentially what happens is that in a person with obesity, that system pushes them to continue over consuming calories to maintain that obese state. And it opposes attempts to reduce calorie intake. And so that's why it's a key contributor to overconsumption, because it's telling you to maintain that higher level of energy intake so that you can maintain that elevated fat mass, which it has decided is what it wants, and this is not conscious. Again, these are like totally non-conscious circuits, just like the ones that are regulating your blood pressure and your heart rate and your digestion. Like, this is not under your conscious control. You're not consciously or morally responsible for what these circuits are doing. This is just a thing that is arising physiologically from your brain, and that makes weight loss difficult and pushes them to overconsume on a daily basis. So that's the homeostatic side of things.
I had one question before you. Before
yeah.
There's a lot to sort of unpack, but I'll sort of rephrase what you said from a meal to meal satiation point of view. And I was curious. It seems what you're describing is brain is trying to estimate calories that you're ingesting while you're having a meal, but it's in sort of an inaccurate estimator. But why is that brain generally is tending to underestimate calories instead of overestimating it? It could, in theory, it should go either way, right? But generally, it seems we are tending to overeat rather than undereat.
Yeah. It's a really good question. I think there are some mysteries that remain, and I don't have a confident answer to this. I can do a little bit of speculating. But I think, these systems are very complex, and they evolved for a very different context than the modern world. These systems evolved for a hunter-gatherer context that existed thousands, millions of years ago. And even these systems actually primarily evolved even long before humans existed, before primates existed. A lot of these circuits, you can find them in lampreys. That is the most ancient living vertebrate, our most distant vertebrate ancestor that separated from us hundreds of millions of years ago. You can find most of this stuff. Lampreys are cyclostomes, which means they don't even have jaws. So this is before the evolution of even jaws. So this is like incredibly ancient, and they already have a lot of the circuitry. So I think that there is an evolutionary context here that is very different than the one that we're currently finding ourselves in. And I think the basic problem is that we have an evolutionary mismatch. We have circuits that are outside of their natural context, and that's causing them to misfire, essentially. And a key aspect of the natural context that contrasts with what we have today is how easy it is to get energy and how easy it is to get calorie dense, highly digestible energy in food. And so I think as a general principle, these circuits are calibrated to tend to err on the side of getting us to eat more, because that was really, not eating enough was a threat historically, was a major threat to survival and reproduction, which are the currency of natural selection. But eating too much wasn't much of a threat. I don't want to say it was irrelevant completely, but it was just a lot less relevant than eating too little. If you think about a hunter-gatherer, you don't, like the modern context, getting food is trivial. As long as you have enough money, I guess. But, for most people in affluent industrialized societies, you go to the grocery store, it takes a few minutes, and then your house is full of food. You can eat tons whenever you want, right? But a hunter-gatherer, if you need to eat, you have to go out and work to procure that food at the time that you want to eat. And so it's a very, very different context. It's not like you can just reach out and grab something and put it in your mouth. And so the idea that they needed to be protected against eating too much is almost like nonsensical. Why would they, how would that scenario even arise, right?
Yeah.
And so I think these systems, I don't want to say that, I do think we actually do have systems to protect us against overeating. I just think they're a lot weaker. They're a lot weaker than the systems that protect us against undereating and tend to push us to err on the side of eating more, because that, evolutionarily speaking, was extremely valuable for our survival and reproduction.
Right. And perhaps this also explains the lipostat system, wherein if the brain knows it's possible to get calories and that's how you've gotten fat, then it would motivate you to sort of get to the level, because it somehow senses that your environment has potential to get you the energy that you currently sort of store in your fat. So it would fight against you trying to sort of shake it off.
Yeah, that's an interesting idea. I mean, I think, so you're suggesting that the brain has a sense of how easy it is to get calories.
Yeah, I mean, when I was reading your book, that's what I was trying to imagine, that perhaps brain has this sense that the environment is rich with food. So it motivates to seek the food whenever the fat reserves go low.
Yeah, I mean, I don't know whether that's true or not, but I think that's certainly very logical. And it wouldn't surprise me if it was true. I think that one of the things we're figuring out is that these systems, even the very, what we used to think of as simple systems like in the hypothalamus and the brainstem that are just kind of regulating energy balance, we used to think, okay, there's these circuits in the hypothalamus. There's a couple of important cell types and they're receiving this leptin signal and maybe one or two other hormones. And it's a negative feedback circuit, kind of like your thermostat. And then that regulates appetite and stuff. But it's turning out that those circuits receive a lot of other inputs. It's actually a lot more complicated than we thought. And so just as one example, these circuits in the hypothalamus that regulate fat mass, they are actually regulated very rapidly by food availability in mice. So if you put food in front of a mouse, if I'm recalling correctly, even before they start eating it, as soon as their brain knows that they're about to be able to eat this food, there's already signals going to those neurons and their activity patterns are changing. And they're basically saying, okay, we don't need to keep seeking food anymore. And so I think that, the reason I'm explaining this is that I think that we are going to continue discovering that there are a lot of inputs that are going into the activity of these neurons, probably from all levels of the brain. And things like, anything you can think of that could have been relevant to energy regulation in the ancestral environment is a candidate for the kind of input that would be integrated into the circuit. Because, if you think about it, just think about it like an engineer. Like, how would you design an animal? You'd probably, in terms of how it regulates energy, you'd probably want it to factor in a lot of different variables into how it's regulating energy. Like, some kind of assessment of the value of the food it's consuming. Like, does it have like certain kinds of toxins in it? If it does, maybe I should only eat a little bit and maintain a lower level of fat mass. Or is it like really great nutritious food, in which case maybe I should eat more of it? How hard do I have to work for it? How abundant? Probably there's like lots of different signals that are impacting the system that we just haven't characterized yet. So what I just said is speculative, but I think that that's kind of the direction that we are going in. And so I think it would be very logical if what you said was true. It wouldn't surprise me if that was the case.
Yeah, I mean, in general, it's really hard to wrap your head around what, say, hundreds of millions of years of evolution can do, especially for a system as complex as a brain and a body, where everything is just going into everything else. I mean, sometimes I even wonder how difficult it is for a science communicator like you to even describe, because everyone wants a mechanistic answer. Our brain is sort of wired to seek simple A to B sort of connections, but in complex systems, almost everything impacts everything else.
Yeah, that's right. And, as a science communicator, like I also, about neuroscience, there's also just a lot that nobody knows and a lot that I don't know. So I just try to respect that. Those limitations. But yeah, I mean, the brain is unbelievably complex. And I think that is something that we're finding, that everything does impact everything else. If you think about, I specialize in the hypothalamus. That's what I was trained in. And even, these circuits that we used to think were pretty simple, they're receiving inputs from a lot of different places. They're sending inputs to a lot of different places. And each one of those places that it's receiving and sending information to is also getting and sending information to a ton of different places. And that's just the hypothalamus, which is a tiny part of the brain. And I'm talking about 2 cell types out of like a dozen that's in the hypothalamus. So thinking about even the complexity of how that even develops during development, how all this stuff gets wired is unbelievable to think that the brain could even exist.
Yeah, I mean, it's so awe-inspiring. But back to the topic, what about these non-homeostatic systems that make us overeat?
Yeah, so I think there are a number of non-homeostatic influences, and I talked about influences on calorie intake, and I talk about a few of them in the book. The biggest one that I focus on is the reward system. And I think this one is really important. This is the system that sets our motivational drive to seek and consume food with certain specific properties. So basically, to state it simply, some food is a lot more seductive than other kinds of food. And that will cause us to seek the seductive food more than the non-seductive food and consume more of the seductive food. And not only is some food more intrinsically seductive, but it has properties that cause our brains to learn to prefer certain things over time as we consume that food multiple times, and also to develop and stamp in certain eating habits. And so that all revolves around a brain chemical called dopamine, which is our learning and motivation chemical. And it's very central to that process, this kind of like intuitive gut motivation to eat, which is independent, or at least partially independent, of hunger, and which we can call craving. That's one way to describe it. And so the way this works, there's actually a lot that's been learned about this even since I wrote my book. And the key way that this works, or a key that the way that this works, is when you consume food, there are receptors primarily in your small intestine that detect the chemical composition of what you ate. And these cells are called neuropod cells. It's a type of enteroendocrine cell, and these cells are directly hooked up to neurons. And when they detect fat, carbohydrate, and protein, they start sending signals to those neurons that send signals up your vagus nerve, up to your brainstem, that tells your brain what you ate. And that signal goes to many parts of your brain, but for our purposes, one of the key places it goes is two places: ventral tegmental area and the substantia nigra, which are dopamine producing parts of the brain. And when those cells detect higher concentrations of fat, carbohydrate, and protein, they start releasing more dopamine into parts of your brain that regulate motivation and learning, particularly your striatum, but also other associated parts of your brain. And what that does, so let's say you ate a slice of pizza that has high concentrations of fat and carbohydrate and some protein and also a lot of salt, which seems to be relevant. You get a lot of activity in this pathway. You get a lot of dopamine release, and then that motivates you to eat more of that. But most importantly, what it does is it sets your future motivational level to acquire and consume pizza. So it causes your brain to learn to be motivated. And the way that works is that your brain will record all of the sensory attributes of the pizza and that situation. So your brain says, I'm going to remember this, cheesy smell and this texture and the way the box looks and where you were when you ate it and who you were with and what the situation was, what the brand was. All that stuff gets stamped in as motivational triggers. And the next time you smell that smell, or you see the box, or you see a slice, or you're walking past that same pizza joint, that is going to get your dopamine spiking again. So your brain recognizes that cue that predicts the acquisition of that calorie-dense food. Your dopamine starts spiking again, and then you experience a craving, a motivational drive to acquire that food. And so that process happens with any food. So it's not necessarily a bad thing. This is just a natural way that our brain motivates us to eat. But the problem is that you get higher levels of reward with more calorie dense foods that combine multiple dopamine spiking ingredients. And so when you have something like ice cream, which has the sugar and the fat, it's particularly combinations of sugar and fat that really drive the system. So ice cream, fried foods like French fries, pizza, cookies, cakes, any kind of like sweet and fatty dessert. Those are the things that really get the system going. And again, it's not inherently bad to have a food spike your dopamine. That's a natural process. But the more dopamine spikes, the higher your level of motivation is to consume that food. And the higher your level of motivation is, the more likely you are to seek and consume that food when you don't really need it. So maybe you would be willing to eat it between meals when you aren't really that hungry, just as a snack. Or maybe you'd be willing to eat it at the end of a meal, like when you're full. So if you imagine, let's say you have, beans and rice for dinner, and you eat as much as you eat until you're full. If somebody put more beans and rice in front of you, you wouldn't eat any more beans and rice. But then somebody brings out a delicious dessert, and suddenly you're ready to eat hundreds more calories, right?
Yeah.
And part of the explanation for that is the very high reward value of that dessert. There's also sensory specific satiety, which we haven't talked about, but we could get into that later. And so, yeah, and let's say the beans and rice was like especially delicious and especially fatty. You're probably going to eat more of that than you would if it was pretty plain and bland and lower in calorie density. So I think that it's not inherently bad for food to spike your dopamine, but the more of that happens, the more it drives your food intake, the stronger the cravings you're going to have, and the harder the harder it's going to be to control your intake. The other thing it does is it causes you to develop habits. So if this process goes on for a while and your dopamine keeps spiking and you're consuming that food habitually, it stamps it in and it becomes kind of automatic. And then that food just becomes a thing that you eat regularly in your diet. So maybe like every day when you're sitting in front of the TV at night, you eat chips. That's just what you do now. Or you have a can of soda in the afternoon. That's just what you do now. And it's just automatic because that rewarding behavior has just kind of become stamped into your brain as a result of repeated reinforcement. And it can be very difficult to change those kinds of deeply ingrained reward-based habits.
Right. I guess, that's what most people call as comfort foods, which is sort of like the default foods they gravitate towards in certain situations. But this brings me to the whole question of food addiction. And I've sort of realized, the more I've read about it, the more I've realized it's a very sort of sensitive topic. Some people think there is food addiction. Some people think there's no food addiction. So what's your view on it? And how common are the mechanisms you just described with other addiction sort of mechanisms such as nicotine or alcohol?
Yeah. So as far as I can tell, all addiction is very similar in terms of the basic mechanism. It is overstimulation of the dopamine system, leading to excess motivation to consume or to engage in a particular rewarding behavior. So all habit-forming drugs, all drugs of abuse stimulate the dopamine system. Even ones that we don't consider harmful, like caffeine, that also stimulates the same system. It just doesn't do it to an extreme degree. But if you look at highly addictive drugs like heroin and methamphetamine, cocaine, crack cocaine, they drive very high levels of dopamine release that lead to very high levels of motivation to engage in drug seeking and consumption behavior. And then you get this reprioritization of behaviors where the most important thing in your life is getting and consuming that drug. Other things like, maybe holding a job and social ties and taking care of yourself just move down in importance because they've been replaced by this thing that your brain now views as the most important because it's been so heavily reinforced by that dopamine. And so this system didn't evolve to make us seek crack cocaine. It evolved to make us seek food and sex and other natural rewards that in the evolutionary context were beneficial, right? The system evolved to help us survive and reproduce, not to make us fat and addicted to drugs. And so, but nevertheless, this is the same system that gets activated by food. And again, that's not necessarily a bad thing. Where it becomes bad is where the activation becomes excessive and starts to lead to negative consequences. And that is what addiction is. If you experience dopamine mediated reward and it doesn't cause negative consequences in your life, then that's not an addiction. So even, some people, there are people who even can use heroin from now and then. And it's not negatively impacting their life. They're using it maybe once a month and they enjoy it. It's not messing their life up. And that's it. And that is not classified as addiction. So it really depends on negative consequences. Yeah. And so coming back around to food, there's two perspectives on this. There's one from the scientific literature and medical communities, and then there's my perspective, which is within the spectrum of opinions in the scientific and medical communities. But I just want to present those two separately. There's no consensus in the scientific or medical communities on whether food addiction is a valid concept. And so some people think, yes, food addiction exists. Some people think we shouldn't be talking about this in terms of addiction, even if people have disordered eating behavior. It's not really the same as having addiction to, heroin or cigarettes or gambling, which is now recognized as an addiction in the DSM-5, which is a American diagnostic manual for psychiatric disorders. And so there's not really a consensus. However, there are, from people who do believe that there is food addiction, there are diagnostic tools that have been developed. So there are questionnaires that you can take, like the Yale Food Addiction Scale, that will classify people as having addiction or not having food addiction. And these are based on the diagnostic criteria for drug addiction. So they basically took those and translated it in terms of food, and then they apply the same criteria. And if you apply those criteria that are established for drugs, you see that food addiction does exist according to this metric. And something like 10% of people in the general population qualify, and then that goes up if you look at people with obesity, and then people with binge eating disorder or extreme obesity, you get to pretty high proportion of people have food addiction. An important point I'll make here is that only something like 25 or 30% of people who have obesity are diagnosed as having food addiction using the scale. So even though that's a higher proportion than in lean people, it's not the case that there's a one-to-one correspondence. So I don't think it's accurate to just say obesity is food addiction. Right. I don't think really anybody believes that that's true. Okay, so that's kind of the scientific and medical communities. My personal opinion, I believe that food addiction does exist. At the most basic level, an addiction is a reward-driven behavior that is causing you harm. And how many people are experiencing harm due to overconsumption of food and consumption of unhealthy food that in part is due to the fact that that food is very rewarding, right? I mean, one of the reasons people are over consuming is because the food is seductive. That is currently in our food environment. That causes people to engage in purchase and consumption behaviors that they may not have otherwise engaged in, just by the nature of how dopamine mediated reinforcement works. And so if we take that very simple definition of reward driven behavior that causes harm, a lot of people, if we just apply that, a lot of people would be classified as being addicted to food. And I think part of the reason people are resistant to that idea is because they don't like the implications of it. They don't like to think about the fact that if we accept that, it means a lot of people have a problem, have an eating problem. And I think that's actually true. That said, I think to some extent, the concept of addiction is not really necessary with food because, well, I shouldn't say it's not necessary. I think it can be important because people who really have a big problem controlling their eating behavior because of craving and reward-driven eating, those people can seek professional help in the form of food addiction treatment programs. So that it does have value in that sense. But I think the thing about addiction is it's pretty arbitrary to call some things addiction and some things not, because motivation is a spectrum. You know, you can go anywhere from being completely unmotivated by a behavior or a stimulus to having such extreme levels of motivation that it's the only thing you care about in your life. And there's an entire spectrum from 0 to 100 that humans can be on. And it's only when you cross a certain threshold that we'll say that's addiction.
Correct.
That we'll label that addiction.
Got it. So since we, since we have only a couple of minutes left, I want to just wrap up and get your views on what people can really do to sort of not gain fat. And I know it's like a very, very big question to ask at the end when we have just a few minutes left, but maybe, one or two top things that you would sort of give very practical recommendations to people.
Sure. So I'll just give a couple of tips based on things that we've talked about. And there's a lot more in my book, a lot more detail and more topics, but a couple of things that I think are particularly important that touch on what we've talked about are, one, eating higher satiety foods. So foods that per unit calorie are more filling, such that you just naturally consume fewer calories while experiencing the same amount of fullness. So this tends to be unrefined, lower calorie density foods that have lower calorie density, higher protein, higher fiber, and moderate palatability. So they don't have to taste bad, but you want to steer clear of those really, really seductive foods. So these are things like oatmeal, other whole grains, fresh fruit, eggs, meat, poultry, yogurt, those kinds of foods, vegetables, and as opposed to more calorie dense processed foods that naturally promote a higher calorie intake. So that's one thing. I think people can get a lot of mileage out of that. So that is properties of the actual food that we're eating. But I think there's another thing that's really important, and that is your food environment. So not just what types of food you're eating, but the food environment that's surrounding you, the kind of cues that you're feeding your brain. And that relates back to that reward system in your brain, that dopamine. And so essentially what you want to do, the key thing is to control the food cues in your food environment. So at home and at work, if you're able to, you don't want to have the sight or smell of foods throughout your day. So you don't want to have food on the counter. You don't want to have it visible, easily accessible, within arm's reach, particularly between meals. And another thing you can do is create small effort barriers to make it a little bit harder for you to get food at times that you shouldn't be eating food. So if there's something that you would kind of wander over to and grab as a snack, put it in a jar with a screw-on lid and put it on a high shelf. Or have the only fruit that's available be the only food that's available be a piece of fruit that you have to peel before you can eat, like an orange. If you're really hungry, you can still eat the orange, but you're not going to just casually stuff it in your mouth. That's something that you have to engage in some effort to do. So controlling your food environment, creating small effort barriers, and eating higher satiety foods, I think that's a strategy that people can get a lot of mileage from.
Fantastic. Thanks so much. I know this went probably longer than what we both were sort of initially discussing, since you are a bit short on time, but I hope you're able to make to your next appointment in time. But this was super wonderful. Thank you, Stephan. It's been a pleasure talking to you. Learned a lot, and hopefully everyone else will learn a lot from the podcast and probably go and pick your book, The Hungry Brain, which I thoroughly enjoyed.
Okay, thanks for having me.
All right, bye-bye. Take care.
Okay, bye.